Welcome back. In this video, we're going to start looking at sequences. Sequences are really cool, and they kind of underpin most of the theory we're going to develop from now on. So we're starting to get into the meat of what we're up to, and we'll find in particular that a particular definition, that of the convergence of a sequence, is one that will kind of serve as a template for a lot of what we're going to do over and over again in this course. Okay, so the question is, what is a sequence? And the technical way to define it is that it's just a function whose domain is the natural numbers. So what that means is, well, let's just define an example sequence. So here are our natural numbers n. They go 1, 2, 3, 4, etc. Then some sequence, and I might call it an, is just going to be some set of numbers that's in correspondence to the natural numbers. So this would be a really basic one. And I'd say something like the sequence an is equal to 1 over n. Okay, it doesn't necessarily have to involve one n in the formula. It could be another sequence, could be bn equals 1 minus 1, 1 minus 1. Okay, there are lots of possible sequences. Essentially, just think of a sequence as a never-ending list of numbers. And technically speaking, you could define that as a function from the natural numbers. Often I'll draw them on some axes just to give us a little bit of graphical intuition. So if we've got n going 1, 2, 3, 4, 5, we might illustrate our sequence by drawing some dots as to how it behaves as we go along. This would be an. Okay, notation wise, generally speaking, I'll use this for a sequence. Sometimes you might also come across this. Just think of the two as completely interchangeable. And now we come to one of our really important definitions, and that's the definition of a sequence, of the convergence of a sequence. So reading it out, we've got a sequence an converges to a real number a. So notice that this number a is part of the definition. Oops, let's not go for black. Okay, so the definition of convergence does not involve finding this number a. It has to be specified. Part of the definition. If, for every positive number epsilon, there exists a natural number n, such that whenever n is greater than or equal to n, it follows that the absolute value of an minus a is less than epsilon, and then we've got some notation to use. Alright, so that's actually quite a mouthful, and it is worth taking a little bit of time to sort of slow down and parse what that means. Because we've got a statement here with 3 different quantifiers in it. If we were to write it in our symbols, we'd write it like, for all epsilon greater than 0, there exists n in the natural numbers, such that whenever n is, that's again another for all n greater than or equal to n, it follows that absolute value of an minus a is less than epsilon. Okay, just to be clear, we actually have 3 different quantifiers going on here. So let's just see if we can express this idea of convergence graphically first to get our head around what on earth is actually going on here. So I'm going to illustrate a sequence. Here's my sequence a, and it's one that converges to a particular number a, and I've been given a, and it's about here. So if I draw a dashed line across, you can see that my sequence is approaching this value, kind of politely. Okay, now a has been given to us, our sequence formula has been given to us, and we just need to understand what this definition means. Okay, so what does this mean? Well, we choose an epsilon greater than or equal to 0, or sorry, greater than 0. Okay, so it starts off for every positive number epsilon. It means that if we're going to go and prove it, we can choose an epsilon. And part of the theorem is there's an an minus a is less than epsilon. Now when we were working with inequalities, we've looked at expressions like this before. That just means we're something about this interval an plus epsilon down to an minus epsilon. Okay, now what this means is I've chosen my epsilon like this, and what it does is it defines a band around my limit point a. And what I'm to find is the existence of some natural number n such that whenever I go beyond it, my sequence terms fall within this band. So the way I think about this is, let's say my n here might be n equals 4. So this is my n that exists, and for everything beyond this n, my sequence terms are confined to this shaded region. Okay, now here's where we get the where we need to think a little bit about these quantifiers, because this n is going to depend on my choice of epsilon. Let's say I made a new choice of epsilon. I'm not going to put it all on the picture because it'll get messy, but if I chose epsilon so that the distance from A was a lot smaller, then my new n, but no, let's sketch it on here in red, that's fine. Okay, there we go. So if I chose a smaller epsilon, then I might have to choose n equals 6 in order for this to be true. And the smaller my epsilon goes, the larger my n is probably going to have to go to match it. Okay. Now, if this sequence converges according to definition, then what it's effectively saying is no matter how small epsilon goes, I can always find a big N that will do the trick, as I've shown here. So even if epsilon is like only a shade bigger than 0, maybe my N is in the thousands or millions or something, but I can still find one that means every term to the right of it will be within the shaded band. So to prove that a sequence converges, I essentially have to follow that strategy. Choose epsilon greater than 0, find an N, or a corresponding N, because typically your choice of N will depend on your epsilon. Find a corresponding N so that An minus A is less than epsilon for N greater than or equal to N. So whenever we want to show that a sequence converges, that is the strategy that we're going to be taking. So let's jump straight into an example and see how this actually works. So I've got a sequence 1 over root n, and I want to show that it converges to 0. Now, to use the definition of convergence, I just need to follow the template that the definition lays out. So it always starts by saying let epsilon be greater than 0. We seek. It's a good idea to get into the habit of writing this sort of template out, just to get really clear what it is we're trying to find. We seek n in the natural numbers. So epsilon has been fixed at this point. It's a fixed positive number. We seek an n in the natural numbers such that the absolute value of an minus a. Okay, so a has been given. A is 0. We're trying to show it converges to 0. An is 1 over root n. For n greater than or equal to n. That's what we're trying to find. So the template for these proofs is always we're going to let epsilon be greater than 0, and then we're going to try and produce an n that satisfies the expression that we need. Okay, so how are we going to do this? Well, I'm going to start by just sort of defining some rough working area. So this is not going to be part of my main proof, but just to get my head around what's actually going on, it helps to start with this expression here and to manipulate it somehow so that we can make it in terms of n. It doesn't always work, but it's a good starting point. So we know that n is positive, so this is really the same as 1 over root n is less than epsilon. Now if I go and mess around with this a wee bit, I'll get 1 over n is less than epsilon squared. Alternatively, I'll get n is greater than 1 over epsilon squared. These are all equivalent statements. We know n is positive, we know epsilon is positive, nothing weird's going to happen. These things are all kind of the same thing. So actually we're saying that this statement here is equivalent to this one here, and this is much closer to what we want. So you can see that if I choose n to be greater than 1 over epsilon squared, right? Because remember I'm trying to choose an n, and it's going to depend on epsilon somehow. Then if n is greater than or equal to n, then it's automatically going to be greater than 1 over epsilon squared, isn't it? And we can show that if we rearrange this, we'll get back to the inequality we wanted before. So that's how our pattern's going to go. This is one that's worth just thinking about a few times over if it doesn't quite click the first time round, because these are not trivial the first few times you try and do it. It does take a little bit of practice to get your head around the various strategies that we're going to employ. So if I go back to my main proof now that this thing converges, it's going to look like this. So I've already let epsilon be greater than 0. I've said something about what we seek. We're going to choose n to be greater or such that n is greater than 1 over epsilon squared. Now the Archimedean principle is the thing that justifies me doing this. I can always find a natural number bigger than any particular real number. Okay, no matter what our choice of epsilon is, 1 over epsilon squared is going to be real, and so that applies by the Archimedean principle. Then, if n, little n, is greater than n, it follows that n is going to be greater than 1 over epsilon squared. Okay, and now if we just go back to our little rough working area, we said these things here were all equivalent. So we can just follow this working in reverse, and this implies 1 over root n is less than epsilon, which is equivalent to the absolute value of 1 over root n minus 0 is less than epsilon. Okay, so our working in the sort of draft phase managed to get us the connection between the statement involving n and the statement involving epsilon. And in this particular case, we were able to follow it backwards and get exactly what we wanted. We'll give you more of these to practice on in exercises, but this is essentially the strategy that all of your convergence proofs will take. It's always set up an epsilon, write something about what you want to find, so we seek n such that blah 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 blah, just to fix what you need to do in your head. And then the hard part is going to be finding, this is the hard bit. The rest of it's usually pretty straightforward. The hard part is producing the right n. For this particular problem, we produced n such that n was greater than 1 over epsilon squared, and we got that from messing around with our inequality to figure out what we needed. Okay, so it's worth doing some practice on these and doing lots of different examples to get a feel for the different types of approaches you can take. Our next theorem says that the limit of a sequence, when it exists, must be unique. Okay, so first thing to note before we actually do that is notice this little bit when it exists. We should note that there are some sequences that do not have limits. So for example, if I took the sequence 1, negative 1, 1, negative 1, and continue on, this doesn't converge to anything. So not all sequences have limits. And the theorem we're about to work on now says that the limit of a sequence when it does exist says that it must be unique. So we are going to just illustrate this graphically and sort of informally prove it by waving our hands a wee bit, but the idea is pretty simple here. So suppose a sequence an converges to some value a and also to some value b where a is not equal to b. Seems like a really weird thing to say because we're so used to talking about the limit of something that to consider the fact that there could be two just seems like a really bizarre thing to try and do. But remember, we've defined convergence to mean a very specific thing. We've set up a definition and we need to verify that the way we've defined it means that we can't accidentally get two different limits just because of some weirdness about how we've defined our convergence. So let's have a look at what this would mean. So I'm going to draw some axes. I'll put A and B on here reasonably far apart so that I've got a bit of space. So remembering what our definition said, I can choose an epsilon greater than 0 so that if I go far enough along in my sequence, I am within epsilon of my limit. So you can see that this is not going to work. If I take a small enough epsilon, such as this one here, and go within epsilon of both a and b at the same time, this is, sorry, b, this will be b minus epsilon here, then my definition says I converge to both of these values if I go far enough across and I'm inside both of these shaded regions at the same time. So if the sequence converged to both of these, then there would be a number n, so that beyond this n, I was in both of these boxes at the same time. Now you can see that's not possible because they don't overlap. And so the way we'd go about it is we'd choose a small enough epsilon, because remember this definition applies for every choice of positive epsilon. And if I can find the choice for which it doesn't apply, then I've shown that convergence doesn't work. So I will choose epsilon such that these things don't overlap, which for us means it's going to be smaller than half the distance between A and B. Then we cannot have absolute value of an minus a is less than epsilon and absolute value of bn is less than epsilon simultaneously. Okay, so that's how the argument would go. And maybe as an exercise you might want to do this slightly more formally just to practice your notation and layout. Okay, so just like for sets, we can define the notion of boundedness for sequences as well, and they apply almost exactly the same way. So the definition says a sequence is bounded if there exists a number m such that the absolute value of xn, our sequence terms, are less than or equal to m for all n in natural numbers n. So first off, note that the absolute value of xn is less than or equal to m is exactly the same thing as writing negative m is less than or equal to xn is less than or equal to m. They mean exactly the same thing. So in the terms of our sequence, what does a bounded sequence look like? Well, essentially it doesn't shoot off to infinity anywhere. Not that we've defined that particularly clearly yet, but anyway, essentially we're saying here's my sequence, here are all the terms, can I find the number m such that my sequence terms all lie between negative m and m. And for this particular case they do, and so you say that m is a bound for my sequence. That's really all there is to it. A sequence is bounded if you can find such a number like this. Okay. So this leads us to the following theorem quite naturally. Every convergent sequence is also bounded. Now this turns out to be quite easy to prove. And again, I'll sketch out the idea graphically first. So here's my sequence. Let's say it converges to some number L. And let's say it's pretty wild before it gets to L. So it's like doing some crazy stuff out here. And then after some period of time, it's going to converge to L. That's kind of my picture of my convergent sequence. Okay, so what I'm going to do is I'm going to say, all right, let's just define an arbitrary number around L. So remember, with our convergence definition, we can choose ourselves an epsilon. I'm just going to choose 1 because it's easy. I'm going to draw my bands in like usual. And so I want to find a bound for my overall sequence. Okay, now if I look at everything beyond my, this would have a corresponding n, just according to what we've been doing before. If I go beyond capital N, then you can see that absolute value of xn is less than or equal to L plus 1, or absolute value of L plus 1 if you like. So the bound is really easy to find for these points beyond my natural number n. But we're saying that the sequence itself is bounded, so how do we modify this part of it? So everything beyond n, finding a bound for that's really easy. It's just my limit plus 1. If L was negative, then it would be the absolute value of that plus 1, which is why I've put the absolute value sign here on. So that's pretty easy, but how do I deal with these points near the start? Well, basically I just say if any of these happens to be bigger, then the absolute value of that can be my bound instead. So this one here, for example, looks to be a little bit larger than L plus 1 in magnitude. So this would be the negative the absolute value of, I don't know, x4, I suppose it is, isn't it, for this one? So in that case, my bound for the entire sequence would be this. Okay, so my entire sequence would fit between plus or minus this value. So that's all we have to do. The fact that it's convergent means we don't need to worry about the infinitely long tail of our sequence, because we've got a bound for those based on our limit of the sequence. And for everything before that, n is finite, capital N is finite. Everything before that, we can just inspect the terms individually. And if there's a bigger one than our bound plus 1, then we make that our bound overall. So how do we put this into words? Well, so let's just write this nicely. Let xn be a sequence that tends to L. We know there exists a natural number n such that absolute value of xn minus L is less than or equal to 1 for all n, actually less than, isn't it? Doesn't really matter. For all n greater than or equal to n. This implies absolute value of xn is less than absolute value of L plus 1. Okay, so that's dealt with all of the tail of the sequence. We just need to find our actual bound, which is just going to be the maximum. Here's where we can express it sort of quite tidily. Let m be the largest of x1, absolute value of x2, all the way up to the absolute value of x, capital N, minus 1. And then the bound that I just figured out, absolute value of L plus 1. It follows that the absolute value of xn is less than or equal to m for all n in our natural numbers. Okay, because we've used the convergence idea to deal with essentially the problem here, which was the problem of having infinitely many terms. The fact that it converges means the infinite part of our setup was dealt with, and as soon as we have finitely many things left over, we can just consider these one at a time, which is what was going on when we look at the absolute value of all of these individual terms leading up to that convergence point. And then the infinite terms all get lumped into this piece here. Because it converges, we know they're all less than or equal to this bound, and so at this point in time, we're finished.